Hi everyone, this is rate laws. So when the concentration of reactants is altered, a change in the rate is expected. So when you double the concentration, you might expect the rate to double. Or if you triple the concentration of the reactants, you might expect the rate to triple. However, this is not necessarily true. And the relationship between the concentration change and how it affects the rate actually must be determined experimentally. You can't predict it otherwise. So what we can design is a rate law equation to help us understand the relationship between the two. Now the m and the n here are actually superscripted. They're exponents. So I'll just rewrite it for us over to the side. The rate law is equal to k, which is called the rate law constant. X is just representing the concentration of ingredient number 1. The exponent m here is going to tell us the relationship between changing the concentration and how it impacts the rate. And then we also have a y, which is the second ingredient, and we're going to raise that one to the n. And again, the exponent will tell us the relationship between changing concentration and how it affects rate. Now, typically, the most common types of reactions only have 2 ingredients. But if we wanted to put a third ingredient in, we could insert a third ingredient. We would actually use Z, and we would put it to the P, not the O, because O looks like 0, and you can actually have an exponent of 0 when we're doing this work. So that's how this rate law is organized. What we're going to be doing is we're going to solve for the M and the N first, then we'll solve for K, and then we'll have a complete rate law that we can then use to solve for the rates, knowing the ingredients and the concentrations going in. So a couple of pieces of definition work. The exponents in the rate law are called the order of reaction. So for instance, if I had ingredient X raised to the 1, I would say that this is a first order in terms of its reaction, in terms of its concentration rate relationship. If the exponent was 2, I would call that second order. The overall order of reaction is just the sum of all the exponents together. So for instance, if I had an equation like this, my overall order would just be equal to 3. I'm just adding the exponents together. So let's get into the tricky bits. The first bit is, how do you actually find those 2 exponents? So what we need to do is we're going to have a set of data that we're going to use, and our job will be to choose two trials where the concentration of one reactant is changing, but the other reactant is staying the same. This will be what we call the change in concentration. And we're just looking for the difference between the 2 concentrations, how much bigger it is or how much smaller it is. Then we're going to look at these same 2 trials for the change that occurs with the rate. Now, the most important piece here is where I've said you're looking at the concentration of one reactant changing, but the other stays the same. And this is because what we're looking for is one piece at a time. What happens to the changing concentration of reactant 1? How does it impact the rate? And then separately, reactant number 2, how does it impact the rate? If we change the concentration of both reactants at the same time, we don't know which one has the influence on the rate. Maybe both of them do, maybe one has a bigger influence than the other, but without separating the 2, we're going to get into trouble there. I'm just going to rearrange our formula once again. So the way we work out our exponent is we're going to look at the difference in concentration between 2 trials, as we mentioned earlier. We're going to raise it to our exponent, so I'm just using m as the example exponent, and we're going to see how that impacts our rate. So it's actually some simple math that we're going to do, but we do have to organize it, and again, make sure we choose those trials, those comparisons really carefully. Once we've solved for our exponents, the second thing we'll be solving for is k. So all we have to do here, it's pretty simple. We're going to substitute one row of basically one row of data from our table that we're going to see in a moment. We'll just substitute one data row in. It'll have everything we need except for k, so we'll solve for k that way. We also have to make sure we figure out what the units are for k, and I'm going to show you 2 ways to do that. One way is we can work it through, just like we work out numbers, we can work out units mathematically, and then I'm also going to show you a shortcut method. Hurrah! All right, so for our first example, we have a balanced equation. The balanced equation doesn't really tell us anything about rate, so it's handy that it's sitting here. We know what the reaction looks like, we know what the ingredients are, the reactants, but that's all it really tells us. So the key information here is the data table. So we're going to have a look at how do we use the data table to turn it into a rate law equation. All right, so we're going to start with reactant number 1. And reactant number 1 is BrO3 minus. So what I want to do, I have 3 trials that have been conducted in a lab where I have changing concentrations for each of the 2 reactants here. What I want to do is I want to pick 2 trials where the first ingredient had a change in concentration, but the neighboring ingredient, ingredient number 2, did not have a change in concentration. So if I have a look, I can compare trials 1 and 2 here because those same 2 trials on the second ingredient did not change. So that is a good choice for working out what happens to rate based on changing concentration of reactant number 1. I'm also going to use those same 2 points when it comes to the rate. I'm going to compare the concentration change to the change in rate. Because nothing happened to those same 2 trials for the second ingredient, I know that the rate change I'm seeing is because of that change in concentration of the first ingredient. So let's work it out. So we're going to work out M first. Remember, that's our exponent that tells us the relationship between concentration and rate, so that's what I'm working at right now. And I'm choosing trials 1, woo, that's not a 1, 1 and 2. So the change in concentration, all I'm doing is I'm going to take my higher concentration and divide it by my lower concentration, raised to the m. Same thing with my rates. So the math here is pretty easy. If the table was reversed and the 2.0 was on top and the 4.0 was underneath, don't worry about it. When you come to put it into this section, you're always going to put the big number on top so that we deal with whole numbers and not in fractions. I know you love fractions now, but we're still going to exclude the fractions for this one. So 4 divided by 2 means that the concentration was doubled. So there's where that 2 comes from. Raised to the m, our rate is 1.6 divided by 0.8. That's also a doubling of the rate. Therefore, if 2 raised to what gives us 2? If you're not sure, play around in your calculator if you need to, but 2 raised to the 1 will give us 2. All right, round 2, we're doing the exact same thing, but this time we're working with ingredient number 2. So once again, my job is to pick 2 trials. This time I want the second ingredient to have a change in concentration while the first ingredient does not. If I have a look, trials 2 and 3 are a good choice here because the first reactant, has no change going on. That means the change in rate I see is only because of what I've done to reactant number 2. That's exactly what I need. So let's work it out. N is the second one. Again, I'm picking trials 2 and 3. Big number on top, 6.0 divided by 3.0, this time raised to the n, 0.8 divided by 0.20. So let's do the first one. That's a doubling of concentration once again, but that is a quadrupling of rate. So 2 raised to what gives us 4? And the answer here is 2. So that means that the second reactant is actually better because if we increase its concentration, it gives us a 4 times increase in rate as opposed to the first ingredient that just doubles if we double. So that's a really important piece of information. If you're working in industry, you're going to want to target your second reactant. All right, so let's write down what we've got so far, and then we'll work out K. That's the next bit. So far we have this. R is equal to K. We know our first ingredient is BrO3 minus, and we figured out its exponent is just a 1. And we know our second ingredient is HSO3 minus, and we know its exponent is a 2. So that's where we are now. So let's figure out what K is. I'm just going to make some space. All right, so when we're working out K, what we need to do is we're going to choose one row of data. I usually choose row number 1, but it doesn't actually matter because one row of data has a rate and it has two concentration values that I need for the two ingredients. So let's put that in just numerically, and then we'll work out units separately. So our R is, let's just rearrange as we go. 1.60 is the R. And we're just going to leave K over here on the right hanging out, and we're going to bring the two reactants across the equals, which means they'll divide. So our first one is 4.0 raised to the 1, and the second one is 6.0 raised to the 2. So let's do the math now. A numerical value for K of 0.011. All right, let's work out the units for K next. So if I do the exact same thing, but this time just with its units, we can work out what that's going to look like. So the units for our rate in the table, I'm just going to pull them right out of the table here. So millimoles per liter times seconds is the one for rate. And then let's do the two underneath bits of this equation. So the first one is a concentration, millimoles per liter raised to the 1. And the second reactant is millimoles per liter raised to the 2. So it's pretty ugly right now, so let's try to reduce it a little bit. So at the top, let's leave that for now, millimoles per liter times seconds. But underneath, I've got the exact same things in the brackets, so I can actually combine them to make the millimoles per liter all to the 3 now. I'm just going to add my exponents together. All right, when I have a fraction divided by a fraction, the rule is to inverse and multiply. So my next step, I'm going to leave this as millimoles liters times seconds, but now I'm going to multiply, and I'm going to do liters cubed over millimoles cubed. So I did two things in one there. I flipped and multiplied the denominator, but I also took the 3 out and applied it to both things inside the bracket there. And that's because the next step that I want to do is I actually want to get rid of some stuff. So for instance, I can get rid of one of the liters on the top and the bottom, and I can get rid of one of the millimoles on the top and the bottom. So the leftovers then, on the top I have liters squared, and on the bottom I usually put it in this order, millimoles times seconds, although if you put the seconds first, I guess that's not terrible. So that's what my leftovers are. So that's a heck of a lot of work, and you can work it out like that every single time, but I am going to show you a shortcut. Alright, so here is our unit shortcut. It always works the same way. Basically, you're going to have this scheme. This could be millimoles or moles, but what's going to change is the exponent. And to find the exponent, you're going to take the overall order minus 1. Let's just see that. So for instance, in this case, you'll notice, let's do this for this reaction. Going back to my rate law, my makeshift rate law here, my overall order of reaction is a 3, minus 1 leaves us with 2. So what I do then is I put a 2 here and a 2 there. Notice that's exactly what I ended up just working out. So the shortcut method will work because of the nature when you flip and multiply, you always end up canceling one of the liters, one of the moles or millimoles. So that's why you always take the overall order minus 1, and it'll always work out for you. Pretty sneaky. Time to put it all together. We have a partial rate law, we have K and the units, and now let's make an actual rate law equation. So we've done all the work now. Let's actually make that rate law equation. Okay. Actually, you know what? I'm going to put those at colons. Hold on. That's better. Okay, so R is equal to 0.011 liters squared millimoles squared times seconds. Then we'll keep this as BrO3 minus to the 1, HSO3 minus. So this problem is a you try it. So I want you to pause the video and figure out your exponents, figure out your K and your units, and then put it all together in a rate law, and then come back and check your work by watching the video. No cheating. Pause it now. All right, I hope you didn't cheat. So for this problem, once again, we're giving a balanced equation. We don't need that. All we need is the table, so we're going to use the table to figure out exponents first, K second, put it all together to make a rate law. So let's start with ingredient number 1, nitrogen monoxide. And again, the job is to choose 2 trials where this reactant is changing concentration, but the neighboring reactant is not, so that I know that the change in concentration applies to just this particular ingredient when I look at the rate. So the best 2 trials here are actually trials 1 and 2. If I have a look next door, trials 1 and 2 do not change for the second ingredient. That means that the change in rate that I see is only from ingredient 1, which is exactly what I want. So N is going to be trials 2 and 3 this time. And again, I'm putting the big number always on the top. So even if they're not organized that way in the table, it doesn't matter. I don't want to deal with fractions. So 200 over 100 raised to the m is going to be equal to 5.47 divided by 1.37. One thing I should mention as we do this, especially when we do this one, we're always going to want whole numbers here, so just round up if you're not quite on the dot. All right, so 2 raised to m gives us 4, therefore m is equal to 2. All right, let's look at ingredient number 2 now. Ingredient number 2, a good choice here would be trials 1 and 2, because if I look at ingredient 1, nothing's happening there, which means the change in rate between trials 1 and 2 are just because of ingredient 2, which is exactly what I want. So trials 1 and 2. So again, big number always on the top. 200 divided by 100 raised to the n is 2 points. Ooh, why did it end up down there? 2.75 divided by 1.37. Eek. Come on, dot. All right, so we've got 2 raised to the n giving us 2. Therefore, n is just equal to 1 here. So let's put together my baseline rate law. So R is equal to K. Concentration of NO is to the 2. Concentration of H2 is to the 1. All right, stage 1 complete, everyone. So let's go to stage 2. Let's solve for K. So once again, I'm just going to take one row of data to solve for K. And it can be the first one, but it could be second or third. It doesn't make a difference. Let's put it in and we'll rearrange as we go. So the rate is the last column, 1.37. I'm going to divide it by my concentrations here. I'm just rearranging as I go. There we go. And that's going to equal to K. Let's crunch some numbers. All right, we're getting a very small K on this one. I've got 1.37 times 10 to the negative 6 for the K. Now let's do the shortcut method for the unit. So remember that the unit is always going to be liters to something, in this case millimoles times seconds. And the thing that I need to figure out is what is the exponent on the liters and the millimoles. So I come over here and I look at my overall order, which is a 3. I subtract 1 to get my exponent, 2 and 2. It's as easy as that. So therefore, my rate law equals actually I'm going to run out of space. Do over. Rate law equals 1.37 times 10 to the negative 6 liters squared, millimoles squared times seconds, NO squared, H2 to the 1. So there is my rate law equation. All right, we're now going to use that rate law we just came up with to try another example, or to try a question with it. So it says, what would be the rate if the concentration of the NO is 0.15 and the concentration of H2 is 0.55? So we now have a rate law equation, which means we can solve for rate. So let's try it on for size. So for this equation, pretty straightforward, we're just going to replace some of the parts with some numbers now. So in this case, the concentration of NO is 0.15 millimoles per liter, and the H2 is 0.55 millimoles per liter. And again, those exponents. So this is where the units can become confusing, but in fact, it's actually easy. The rate law, the K value, has actually made it so that whatever we get at the end should be the right example or right unit. So for instance, rates will be the same as it was in the table. It'll be millimoles per liter times seconds. And the units will all work out here because of the work we did with the K units. So let's come up with a number and a unit. I'm getting 1.7 times 10 to the negative 8 millimoles per liter second. We should probably keep an extra digit, so let's throw a little 0 in there. This is the last of you try it. So again, you're going to pause the video. No cheating. You're going to have to try it by yourself. This one's a little more complicated because we actually have 3 ingredients this time instead of 2. That means you're going to have to be really conscientious when you're picking your trials, because now you want, again, one trial to change each time and the other 2 must not change. All right, you better have tried this by yourself before watching this video. Let's go for it. So we're starting with we'll call it A, ingredient A, as they do in the table here. And I would say we're going to choose trials 1 and 2 here because, again, if I look at the trials 1 and 2 for ingredient B and C, no change, which means the change in rate I see going on is just because of A, which is exactly what I want. So exponent M will be trials 1 and 2. Big number on top as always, 0.0200. Divided by 0.0100 raised to the m gives us 0.00483 divided by 0.00242. Let's crunch some numbers. So this is just 2 raised to the m gives us 2. Therefore, m is equal to 1. All right, reactant number 2, choose the trials. So I would say we're going to choose 1 and 3 here. If I look at the neighbor A, 1 and 3 does not change, and C, 1 and 3 does not change. That means the rate that I see going on here is just because of what I'm doing in B, and that's exactly what I want. So this is exponent N. We're going to do trials 1 and 3. So again, big number always on the top, 0.0200 divided by 0.0100 raised to the n. 0.01936 and 0.00242 on the bottom. So this one has a huge impact on rate. 2 raised to the what gives us 8, n is equal to 3. All right, we've got one more here, and again we're looking at C this time, and I would choose trials 1 and 4. Again, if I have a look at 1 and 4 for ingredient A, no change. Ingredient B, no change, which means that the rate I'm seeing here is because of what I'm doing to C, and that's exactly what I want. Again, I'm going to call this exponent P, trials 1 and 4 here. Let's set it up as always. So 0.0400, big number always on the top, raised to the P, and we've got 0.0. All right, let's work it out. So here we've got 2 raised to the p equals 4. Therefore, p will be A2. So let's put our basic rate law together down here at the bottom. So we've got R is equal to K, A is raised to the 1, B is raised to the 3, and C is raised to the 2. All right, stage 1 complete. Time to do stage 2, come up with our K. All right, we know what to do. Take one row of data, sub it in. So my rate is 0.00242. Don't worry about units right now. We're going to divide because all of those concentrations are going to come across the equals here. We've got 0.100 raised to the 1. Same thing for B raised to the 3. Different value for C raised to the 2. And let's crunch some numbers. I just found my mistake. Hold on. Hold the phone. You're probably yelling at the video right now. Just calm yourselves, people. Calm yourselves. Don't worry. I figured it out. All right. I'm getting a big number this time for K. 6.05 times 10 to the 8. And let's work out the units using our Cheaty method. So again, it's always going to be liters over, in this case, millimoles, according to our table. So it's kind of like the inverse of the rate units here. And then again, we need our overall order minus 1. So we've got 4, 5, 6 in total. Minus 1 gives us 5. So 5 here and 5 here. So grand finale, our rate law is 6.05 times 10 to the 8 liters to the 5 millimoles to the 5 times seconds. It's getting a little ugly here. dot. All right, A to the 1, B to the 3, C to the 2. Woo, we did it. All right, the last of the questions here are using that rate law. So the first part is, according to your rate law, which compound should you increase the concentration of to get the fastest overall rate? As we can see, B would be our winner here, because every time we increase our concentration of B, we get a 3 times increase in the rate. It is an exponential relationship there. So definitely the one with the highest exponent is giving us the highest payout. So increasing concentration gives us a 3-fold increase in rate. In part B, it says calculate the rate if the concentration of the ingredient you chose above is 0.5 and the others are 0.25. All right, let's do some substituting. So R is equal to 6.05 times 10 to the 8. Let's just leave our units for now. The first one's going to be 0.25. The second one, the one we chose, is going to be 0.5. And then the last one is also 0.25. Let me put my exponents in before I forget them. There we go. All right, time to crunch some numbers. 1.18 times 10 to the 6 there for the rate, and my rate will be the same as the unit in the table, so millimoles per liter times seconds. Nothing fancy there. All right, in part C is calculate the rate if the concentration above was reversed, and the ingredient from part B is 0.25, and the other two ingredients are 0.5. All right, let's substitute and solve. Time the 0.25s will become the 0.5, and the 0.5 will become the 0.25. Let's find out what that happens. And the answer is, it's the same answer. But what I realized in the last example is that I should have taken it to 1.2 times 10 to the 6. I'm going to make that correction up above, because of course, we were given just 2 significant digits. So I'm going to just fix that. You're probably yelling at the video, but too bad. All right, there we go. Practice time. Oh yeah, so much fun.